Yes. So, in our last discussion, we have been doing static logic with CMOS. So, static logic, as we have already discussed, it is a complementary logic. This complementary logic, you won't be able to implement a normal function out of it. So that is, what you are getting is, if I am having A and B as the input, my output is AB the whole bar or A plus B the whole bar like. So the complementary output is the result. So when I want to when the implementation is for an AND gate, so the AND gate implementation, so static logic, this AND gate, there must be two NMOS which forms our input A and B, and which forms the pull down network. This is my ground. This is my PMOS. This is my A and B. So this is my VDD. These things you know. I'm just refreshing it. So here what I am getting is AB the whole bar, 2 input NAND. That's what I said. This is a complementary logic. From here I want to invert this. So my intention is to have so you see, this is my AB. This is my AB, that is my AND gate. So in order to implement this AND gate, how many transistors I do require? So number of transistors is 6. 6 transistors I want. 6 transistors I want. So this is true for almost all implementations with static logic, if our implementation is normal implementation, not complementary implementation. So let us see how pass transistor logic is beneficial in this context. So our discussion today is in fact pass transistor logic. So I want you to compare this with pass transistor. That's why I have drawn this picture first. So pass transistor logic. So in our syllabus, this forms the fourth module of our syllabus. Pass transistor logic. Pass transistor, basically it is an NMOS logic. This NMOS logic means this is an NMOS transistor. This is an NMOS. So NMOS, this is a control terminal. If this is B, this is my input A. So we know when this B is 1, this transistor is on. So whatever things you are placing at A, at this input, that will be passed. If you are placing a 1 at A, that will be passed. So if you are placing a 0 at this point, that will be passed. Provided your B, this control input is 1. If control input is 0, so this transistor will be idle and that won't pass anything. So this is a simple pass transistor logic. Pass transistor logic is an NMOS logic. If I am cascading this, if I am having two pass transistors like this, so I am having this control terminals, okay. So this is my A, this is my output Y. So this output, let this output be Y2 and this output be Y1. So this Y1 is, if this voltage is, this is 2 volt, let this be 2 volt. I am placing 2 volt at this point, and this control terminal is C is high, C is 1, and I am placing a 2 volt. If the threshold voltage of this transistor M1, that is 0.7 volt, if it is 0.7 volt, threshold voltage is 0.7 volt, my Y1 is input minus this threshold voltage, that is 2 minus 0.7, that is 1.3 volt. When it reaches Y2, again if this transistor M2 is having a threshold voltage of 0.7 volt, the point Y2 will be having 1.3 minus 0.7, that is 0.6 volt. That is obviously a disadvantage of this kind of logic. So there are ways to overcome this. We will discuss that ways to overcome this problem is, we will discuss it later. So we are going to the implementations using pass transistor logic. So the concept is, this is a pass transistor, this is an NMOS logic, this is basically an NMOS transistor. If the control terminal is 1, whatever input you are placing, that will be passed to the output. That's a very simple concept. That's the only thing you must remember. Everything else, this is the problem of pass transistor. When it is cascaded, so the output will be having a diminishing factor of the threshold voltage. So it will be the input minus threshold voltage. So that poses problem, or definitely we will discuss in another this problem in another session. So let us elaborate the implementations using pass transistor logic. So the next point is, we are implementing a 2-input AND gate using pass transistor. Two-input AND. So it's a 2-input AND. Definitely there are 2 inputs, A and B. So okay. Okay, this is B and this is B bar. This is my A, this is my B. You join these 2 points and this is my Y output, and let us see the outcome of this. See, this is A, this is B, and this is my Y. Since there are 2 inputs, there are 4 cases. So this could be 0, 0, this could be 0, 1, this could be 1, 0, and this could be 1, 1. When both inputs are zeros, so both inputs are zeros, so this input is 0 and this input is 1. And this transistor, let this be M1 and this transistor be M2. So obviously this M2 is on, whatever input you are placing at B, that will be passed, so your Y will be 0. Y will be 0. And when your input is 0, 1, your input is A is 0 and B is 1. See, this is 1. And this input is 1 and this B bar is 0 then. B bar is 0 then. So this transistor is on, so this 0 will be passed. So this 0 will be passed. Similarly, for 1, 0, it will be 0. And when it is 1, 1, these both inputs are 1. So this is 1 and this is 0. And your Y will be, this transistor M1 is on now. So this A input will be passed and this is 1. See, watch this output Y. When both inputs are high, your output is high. That is nothing but Y equals AB. That is nothing but your AND gate. AND gate. So obviously, what is the advantage? So we have started this discussion with what you call static logic, static implementation of AND gate. So there we record 6 transistors. In place of the 6 transistors, here the core implementation consists of 2 transistors. And if you want to, we have to make B into B bar, that requires another 2 transistors. So obviously your requirement is 4 transistors. So from 6 transistors to 4 transistors, it's a saving of space. So far as your implementation in a chip is concerned, so we know the area is reduced. That's advantage, and we will continue this discussion for other implementations. Thank you.